In this unit, we started by talking about momentum and its relationship to the mass and the speed of the object. Then we moved into looking at the impulse and how we change that momentum. Today, we're going to look at the conservation of momentum. Like all conservation laws, what we're looking at is what happens before an event occurs and what happens after an event occurs. And where we're heading with this is we're looking at the collision of two objects. And the conservation law says that when you look at the amount of momentum you had before the collision, it should equal the amount of momentum you have after the collision. And I say should. In practical world, there's always a loss of energy, but we're going to go with an assumption that 100% of the momentum is transferred from prior to the collision to after the collision. Now we're going to focus on one-dimensional collisions, and we'll save the two-dimensional and three-dimensional for future courses. So I've got my two carts here, each with a mass, and I can push them to cause a certain velocity in their motion, and that'll give each of these carts momentum. What we're going to work on is imagine if these carts were both moving in the same direction. Let's say it's moving north, or maybe it's moving south, but we're not going to have one moving north and one moving west. Okay, that would cause us a two-dimensional collision, and that's not what we're going to work on in Physics 11. So what we have to think about is what would happen if the carts were moving in opposite directions, one moving north, one moving south, and collided? Or what if they were both moving in the same direction and collided? My two carts. Cart A has a mass of 1 kilogram and is moving at a speed of 3 meters per second. Cart B has a mass of 2 kilograms and is moving at a speed of 4 meters per second. We can easily find the momentum of each. So I'm going to say the momentum of A would be its mass times its velocity, which would give us 3 kilogram meters per second. The momentum of cart B would be the mass times the velocity of B, and that would equal 8 kilogram meters per second. So the next thing we need to do is figure out what's going to happen. Are the carts going to move towards each other, or are the carts moving in the same direction? If they are moving in the same direction, we would combine the two momentums to have a momentum total before the collision of 11 kilogram meters per second. But if they're moving in opposite directions, the momentum of one will cancel out much of the momentum of the others, and we end up with a total momentum of 5 by simply subtracting the two momentums. So once again, if they're moving in opposite directions, you're going to subtract, and if they're moving in the same direction, add them together. We figured out how to find the total momentum, so let's use that into solving a problem. Here I see a train car, and it has a mass of 1,000 kilograms, and it's moving west. So I'm going to indicate moving to the west. I'll call that to the left. So we'll say that this is west going that way, and it has 1,000 kilogram mass, and it's moving west at a speed of 8 meters per second. Okay, or a velocity because I've given direction. I have another car with a mass of 3,000 kilograms, and it is also moving west, and it has a velocity of 4 meters per second. Now, I had to draw the cars this way because if the faster car was in front, it would never catch up. If I want to have this car here crash into that car, this has to be the faster car. So I just put that one in back. So what I'm going to do is I have to figure out what is my total momentum of each of the cars and get my total momentum before the collision. So what am I going to do? Let's call this, I don't know, we'll call this one car A over here. We'll call this car B. So the momentum of A, oops, I wrote B. The momentum of car A is the mass of A times the velocity of A. Wow, I keep writing B, of A. So what we have here is we have 1,000 kilograms being at a speed or a velocity of 8 meters per second. So the momentum of car A is 8,000 kilogram meters per second. What about the momentum of car B? Well, once again, it's the mass of B times the velocity of B. And the mass of that car, it's 3,000 kilograms. And it was moving at 4 meters per second. So it has 12,000 kilogram meters per second. So now the question is, what is my total momentum of everything? What's going on before they collide? Well, the question is, are they going in the same direction or are they going in opposite directions? And they're both going in the same direction. So we're going to add those together. So I'm going to say that my total momentum is 20,000 kilogram meters per second. Okay, so that is my total momentum before the collision. Okay. Once again, please note, they're both moving in this direction. So what's going to happen after they collide? Well, after they collide, they're both going to be moving in this direction, but they're going to be hooked together somehow. They got Velcroed together, and they are still moving in the west direction, and they're going together. Okay, so that's the first thing. The next thing is, this is the conservation law right here. The amount of total energy before the collision equals the total momentum after the collision. I'm going to put a little symbol here. It looks like a little 1. That's called prime. Okay, that's a prime symbol. Okay, that little 1 right in there. And what that is meaning is that just means after the collision. So the momentum before the collision, the total momentum in the system, is the same before the collision as it is after the collision. Okay? So now what we know is that our momentum law hasn't changed. Our P prime equals the mass times the velocity. And I'm going to use the prime symbol here again, just to represent that it's something happening after the collision. Well, I know that this 20,000 kilogram meters per second is equivalent to the mass. Well, what is the mass? Well, now because these two cars are hooked together here, we have a mass of 4,000 kilograms. So this is going to be mass of 4,000 kilograms times its new velocity. I don't know the new velocity, but easy enough. I can take my 20,000 kilograms meters per second and divide that by the total mass, which is 4,000 kilograms. And I'm going to see that I have a new velocity of 5 meters per second west. Okay, or in that direction. Once again, key concepts here. Make sure that we know our formula for momentum. We just keep applying that formula over and over. In this particular example, we used it 3 times. And this right here is the critical piece. This is our conservation of momentum. Okay, the energy, I'm going to call it energy, it's not really energy, but the amount of momentum in the system before the collision is exactly the same number as the momentum in the system after the collision. Scenario, and although initially it looks very similar, it does have some significant differences. Once again, I have a train with a mass of 500 kilograms moving west. So I'll make that this car over here, car A, moving west. And it has a velocity of 10 meters per second. And it has a mass here of 500 kilograms. Okay. I have another car, car B, but car B is moving east. Okay, so car B moving east, and it's not going very fast. It's at 3 meters per second, and it's quite a bit heavier here at 2,000 kilograms. Okay, so I want to know what's going to happen when these two collide. Okay, so once again, I'm going to calculate the momentum. I'll do B on this side. So this is B is going to be the mass of B times the velocity of B. And over here, I've got the momentum of A is the mass of A times the velocity of A. Once again, here I have, let's put the mass first, 2,000 kilograms. And it's 3 meters per second. So this has a momentum of 6,000 kilogram meters per second. On this side, I have a 500 kilograms moving at 10 meters per second. So this is going to have 5,000 kilogram meters per second. So when I figure out my total amount of momentum in the system prior to my collision, so my P total, because they're going in opposite directions, we're going to see a significant canceling out of energy. So what you do is you subtract the two. So we're going to subtract the two, and I'm going to have a total final momentum before they collide. We're going to say it's before they collide, but I mean, obviously this doesn't happen until they collide, but we have a total of 1,000. The question is, in what direction? Is it east? Is it west? It's not going to be north or south. It's going to be either this one overruns that one or this one overruns that one. And because the bigger value is over here, it's going to have a net momentum in that direction, which is the eastern direction. Okay, so my P total is 1,000 kilogram meters per second heading east. Well, what's my total momentum after collision? And once again, this is the critical part. This is my conservation law right here. This is the conservation, okay? Conservation of momentum. Momentum, okay? Whatever we started with, this 1,000 before collision, we have 1,000 after the collision. And it's in the same direction, it's east. Okay, so what we can do is we can figure out, we can say, well, our total momentum after the collision is equal to the mass after the collision multiplied by the velocity after the collision. Okay, let's see. We know that this is 1,000 kilogram meters per second. What is our mass? Well, our mass is going to be 2,500 kilograms. And it's going to be multiplied by whatever that velocity is. Remember, this isn't like an exponent. This is just, it's a symbol to say after the collision. Okay, so our velocity is going to be 1,000 kilogram meters per second divided by 2,500 kilograms. So our velocity, I'm looking at my units here. I see the kilograms on top, the kilograms on bottom. I'm going to be left with meters per second. So it's going to be that. And once again, remember, it's going to be in this eastern direction. Don't forget to give me your direction. It's going to be moving east. And let's see, what's 1,000 divided by 2,500? That's like 0.4. Should I get out my calculator? But I think that's like 0.4 meters per second. So in the end, when those two collide, they're going to be moving at 0.4 meters per second to the east together.